Hello everyone. So in this video, we will discuss the relativistic covariance of the Maxwell's theory of electrodynamics. Okay, so we have seen that the first postulate of relativity tells us that any good theory of nature must be relativistically covariant, which means that any any inertial frame we go to, which are related by, let's say, constant boosts, like which are moving with respect to each other with constant velocities, our theory, the form of our theory should remain invariant. So the mathematical way to ensure this would be to write down the equations which determines the dynamics in our theory in terms of scalars or four vectors or four tensors, so that our theory is covariant. That means, no matter which frame we go to, the form of the equation remains unchanged. Okay, so therefore, we have studied electrodynamics in this form where we have written down the Maxwell's equations in terms of three vectors or three-dimensional vectors, right? So these are vectors along the spatial directions. So our challenge now is to be able to write the same equations, or rewrite these equations in the language of four vectors, or four tensors rather, thereby ensuring that the Maxwell's theory of electrodynamics is relativistically covariant. So this is what we are going to try and accomplish in this video. So let us start with the Maxwell's equations. So you are familiar with this form of the Maxwell's equations. Here I have particularly grouped the Maxwell's equations in such a way that I have written the Maxwell's equation with the sources separately, and the other two Maxwell's equation without the sources, which means the Faraday's law and the divergence of B equal to 0, that equation, those I have written separately. And of course, there's a current conservation equation, or the conservation of charge equation. This is written in the local form in this way. Okay, so basically, once we have this equation, we have seen that we can write the electric and magnetic field in terms of a vector potential and a scalar potential, right? So as soon as we write the electric and magnetic field in this form, these two equations are solved. That means they become identities. All right, and that is precisely the reason why I have written them separately. And you will also see that these equations in the relativistic picture group together in the way that I have written down here. So that is what we are going to see in this video. So apart from this fact, there is also this notion of gauge redundancy, which we have discussed, and this tells us that if we change the potentials in this way using some other scalar field chi, then the expression for the electric and magnetic fields remain invariant, because if I take this and plug it in here, then these expressions become independent of chi. Okay, it's basically invariant under these gauge transformation. Okay, these set of transformations, and so are the Maxwell's equations, because the Maxwell's equations are written in terms of the electric and magnetic fields. So the Maxwell's equations are also invariant under gauge transformation. Okay, so basically we would like to see now how to express these set of quantities in terms of or as relativistically covariant quantities. That means they are like four vectors or four tensors or four scalars. That's what we want to see. So in order to do that, so of course the players in the game, that is not going to change. These are going to be the players in the game. It's just that they are going to fit together, maybe different. So of course we have a vector here, for instance, and a scalar field here. So, so when I say a vector field and a scalar field, I mean this is a vector in terms of rotation and scalar in terms of rotation. Now, we would like to write down quantities that are four vectors or four scalars. That means they are, when I say a four scalar, that means they are a vector which transforms covariantly under both rotations as well as boost transformations. Okay, that means they are vectors of the full Lorentz transformation. Okay, so that's what we need to do, and therefore, as you can anticipate, the three components of these three vectors, they have to combine with something else. So I have to say what the fourth component is, so that they can form nice four vectors. Or let's say if they are scalars, then they can remain as scalars in terms of both boost and rotations. But essentially, the idea would be to take these players in the game and combine them into vectors and tensors in 4 dimensions, whereas these equations are expressed in terms of vectors and tensors in 3 dimensions. Okay, so we have to perform that combination. Okay, so this is how it is done. So the first starting point is to realize, and this is probably what else can it be kind of an argument. Let me not try to motivate much about this, that the three components of the vector potential and the scalar potential, they together form the 4 components of a 4 vector potential. Okay, so this is the 4 vector potential whose time component is this phi. Okay, the 0, as you know, the mu index runs over time and the 3 space components. So the time component of the 4 vector is this scalar potential, and the space component remained as the previous vector potentials. Okay, so this is more or less our starting point. Okay, and apart from this, the current density also has a natural candidate. So if I try to write down the 4-dimensional current density, then we see that there's a vector current. This is the vector current density. This is the original current density. Okay, the one which we called originally as the current density. That one is there, and then there's the charge density. So these two things can fit in together to form a 4-vector current density. Okay, this is what it happens, and the factors of C, as you can see here, are put in for dimensional reasons. Okay, so essentially, much of this discussion is convenient to do if we work in natural units where the C is equal to 1, but I will try to keep track of the C as much as possible. Okay, so I'm trying to say everything in SI units, so I will also try to discuss this relativistic electrodynamics also in SI units. Okay, so that for that, if I have to do that, then the C here compensates for the difference in dimension. Very good. Now, so this is the main, if you like, this is how the potentials group together into a 4 potential, and the charge density and current density group together to form a 4 current density. Okay, so this is the form. Now we can start by trying to understand how to write down the electric and magnetic fields, or how to group them together. Because for the electric and magnetic fields, there are always like 3 components. Okay, so it's not. Of course, they have pretty much the same status in some sense, but they are like 3 components. So there are in total 3 electric field and 3 magnetic field components. So there are like 6 objects. Okay, so that cannot really become a 4 vector in any way. Okay, even if you put them together, and if you don't put them together, there is no natural thing which you can add to the 0th component of the electric field to make it a 4 vector. Okay, so that's not what happens, but what happens is the following. Okay, what happens is the following. So basically, the hint is derived from the fact that the vector potential is given, gives the magnetic field. When I take the curl of the vector potential, I get the magnetic field, right? So you might want to try out and see that if I take the 4 vector potential and write down its 4 curl. So as we have discussed in the previous video, this is the expression for the 4 curl for the 4 vector potential. Okay, so if I write that down, I get a new vector, I get a new tensor, okay, and this tensor is basically the 4-dimensional curl of the 4 vector potential, okay, and let us study what this tensor is. Okay, let us study what this tensor is. Okay, the first thing that we want to know or we want to observe about this tensor is that it is antisymmetric in these indices mu and nu. That means if we interchange mu and nu, okay, then I should get a minus sign. What do I mean by that? What I mean is, let's say I have F01, then that should be equal to minus F10. Okay, that's what I mean. Okay, the components are identified. Okay, the these two components have the same magnitude, but they differ by a sign. Okay, that's what I mean by this tensor is antisymmetric. Okay, so good. Now, if I have an antisymmetric tensor like this in 4 dimensions, so this is as I have written it down. You see, this is a 0, 2 tensor, but 0, 2 antisymmetric tensor. So let us see how many independent components it would have. Let us think of the first index to be the row index and the second index to be the column index, so that F mu nu can be thought of as a 4 cross 4 matrix like this, right? So I can do that. I can of course do that. So if I think of them that this as a 4 cross 4 matrix, then the number of independent components in that matrix is going to be of course 4 into 4 minus 1 by 2. That's 6. There are 6 independent components of this quantity, which is basically to start off with is just the curl of the 4 vector potential. Okay, so of course there are 6 such quantities. Okay, 6 independent quantities. Now we also observe the fact that the electric and the magnetic fields put together, they also form 6 components. They have 6 independent components. So there are 6 quantities to worry about there. And also these, when we take the curl, there are derivatives, there's time and space derivatives that act on the potentials, right? We know from the expression of the electric field and magnetic field that they are given by one derivative acting on the potentials like this. Okay, so basically this seems that it could be related to the electric and magnetic field. So let us try to write down the components of this F mu nu vector, F mu nu tensor, and see what they come out to be. Okay, so if we try to write the components down, then so here is my notation. I'm writing out that F0i meaning the first index I have set to be time. Okay, that's the 0th index. And then the I, so I'm distinguishing this. The mu and nu runs over 0, 1, 2, 3. Okay, so it runs over the space-time components, whereas the I and j, these levels run over 1, 2, 3 only. Okay, so this is how I distinguish in some sense between space and time notations. Okay, so this is like a 4 vector notation. This I'll denote with mu and nu, and this is like a 3 vector notation which we have been doing, and I'll denote it with I and j. Okay, so now this 4 vector here, this tensor here, this antisymmetric tensor here, if I look at the time and any space component of it, then I will write this thing down. Okay, 0 ai del I a0, and as you can simply see here, this comes out to be exactly the 3 components of the electric field as I runs over 1, 2, and 3, because this object is just going to give me the gradient of the, so this object is the gradient of the potential, this term. Okay, and this object is the time derivative of the vector potential, this term. Okay, so simply this F0i, this forms the 3 components of the electric field. So as soon as I know F0i, I immediately know Fi0, because this is just minus of this thing. Again, the C hangs around because I have put it into the definition of mu. One thing is very important I would like you to note. So mu with the upper index, that means the vector mu, that is defined as the potential and a vector. Okay, but the mu with the lower index, which is the corresponding covector, which you obtain by multiplication with the metric, as we have seen in the previous video, then this my metric, essentially my metric convention is eta is basically diagonal plus 1 minus 1 minus 1 minus 1. Okay, so with this convention, with this convention, the spatial indices here, they get a minus sign. Okay. So I hope there are so many A's, it's not confusing. I'm using the same notation. I hope it is not confusing. I am using the A notation to denote the 4 vector potential as well. Okay. And it's not only the vector potential, the co-vector potential also I'm using the same symbol, but you can distinguish between them by noting where the indices are, whether it's an upper index or a lower index. Okay. So it might appear when I wrote this term down, I meant it is the component, the ith component of AI. But then you might think that why am I putting in this minus sign? It is because the ith component of this AI, the ith component of this AI, is basically minus AI. Okay, so that accounts for this minus sign here. I hope it is clear. Okay, I hope it is clear. Let me write it here because this can cause a little bit of a confusion. Okay, let me write it here to remind you that A nu is basically phi by c minus a vector. Okay, and that basically is responsible for this sign here. This minus sign is responsible for the sign here. Okay, so don't just think that I have made a error in the step, just putting in a additional minus sign here. This minus sign comes around. Unfortunately, in this way of writing, this too has the same notation here. Okay, but they are different objects. This one is the vector potential. That is what I'm calling, this A vector component, and this is the ith component of the co-vector 4 vector potential. Okay, so I hope this point is clear. Okay, and it doesn't cause any confusion. It is a potential source of confusion. So if you like, I can use. You could have used a different symbol for this, but I'm refraining it from doing so because one can keep track of this, and one can try to keep the sign in mind and work with the right sign. Okay, so this is one very important point about convention and notation. Next, let us try to see what are the other components of this F tensor. Okay, this antisymmetric tensor. What are the other components? So if you write down the ijth component, again I have a I and a j and I. Okay, this is simply given by, so let's say x and y component. Okay, so this is x ay del y ax, but again there's a minus sign because again I'm talking about the co-vector and the spatial components get a minus sign. Okay, that is why I have a minus sign here. Okay, so this minus sign you have to be a little careful about. Okay, because of the kind of notation I am using, please be careful about this minus sign. So as you can see, this object is nothing but the z component of the magnetic field with the minus sign. Okay, so this is the z component of the magnetic field, and similarly if yx, that component is just minus of this, so that is equal to just b of z. Okay, very good. So similarly, you can work out all the ij components for x, y, and z. Okay, that's what I mean by 1, 2, and 3. And you will see that these component works out to be the components of the magnetic field because it's just the curl of the 3 vector. Okay, it's just the 3-dimensional curl of the 3 vector. So this comes out to be the components of the magnetic field. It just works out. Okay, please don't get confused with this change. Okay, again let me emphasize this point here. Okay, let me emphasize this point here that this sign is basically this sign here. Okay, so hopefully that is clear. Okay, so very good. Now if I write down the matrix, of course the diagonal components have to be 0 because it's an antisymmetric. Okay, so the diagonal components have to be minus of itself, so that has to vanish. But the 0i and the I0 components, they are the electric fields, and the rest of the components here are the different components of the magnetic field. Okay, so this is the structure of this object, and therefore we conclude that the electric and magnetic fields together, they transform like the components of a 0,2 tensor. Okay, we know how a 0,2 tensor transforms, and therefore that we have discussed before, okay, in the previous video. And so from there, it would be very easy to work out the transformation properties of the electric and magnetic fields, given this tensor is the various components of this tensor are essentially the components of the electric and magnetic field. Okay, so this is a very, very important result, and this tensor here is called the field strength tensor. Okay, so from now I will refer to this tensor as the field strength tensor. Okay, so that's your field strength tensor. Now, apart from this field strength tensor, there is one other tensor which is also composed of the electric and magnetic fields. In fact, it is expressed in terms of the field strength tensor only, because in 4 dimensions you have this epsilon or this Levi-Civita. Again, with the help of this Levi-Civita, it is possible to construct another tensor which is F tilde. Okay, where you can see these are the 2 mu nu indices, these are the mu nu indices, and this lambda sigma indices are contracted with the lambda sigma indices here. That means, they run over 0, 1, 2, 3, 4, and they are summed over. Okay, so that is basically the bottom line. That this is another another tensor which is very much like the field strength tensor, but because of the epsilon here, the components are arranged in a different way. Okay. So again, let me mention one quick fact that also has come up in a discussion in class, that this Levi-Civita tensor is not a proper tensor in general under general coordinate transformation. But as long as the matrix is this diagonal matrix, this +1, -1, -1, -1, and we are talking about only linear transformations like boosts and rotations, then for that, this epsilon behaves as a tensor. Okay, so you can go and verify it. You know how the tensor should transform. So this is like this one is like a 0,4 tensor. Okay, it would transform like a 0,4 tensor. Okay, of course, if you are doing general coordinate transformation and your matrix is different than what I wrote down here, that it's a function of x and y and z and time. That can be when you're talking about, let's say, scenarios in general relativity. And in that case, this epsilon is not a tensor anymore. It's a tensor density, and it has to be appropriately divided by root over the determinant of the matrix, root over minus the determinant of the matrix, to make it transform like a tensor. So the bottom line is that for the specific case that we are interested in, epsilon, this Levi-Civita symbol is also a tensor. But more generally, there can be a completely antisymmetric tensor that can be constructed out of this Levi-Civita symbol by multiplying or dividing with the appropriate factors of root over minus the determinant of the matrix. Okay, so it is always possible to find a tensor quantity which is completely antisymmetric, constructed right from the constructed just with plus and minus ones and zeros, and just with the determinant of the matrix. Okay, so here the determinant of the matrix, root over minus determinant of the matrix, that's just 1. So in this case, we'll not worry about that additional complicacy, and we're going to treat this epsilon as a proper tensor. Okay, so with that, we find that if this has tensorical properties, then we can take this also has tensorical properties. So when I perform this contraction, this is also another covariant object, and this is also like a 0,2 tensor. Okay, you can check the transformations, and it turns out to be a 0,2 tensor as well. Okay, so basically this is what we find, and right. So this F tilde, this is almost very similar to the field strength tensor, but as we can see that it is going to be an object where the electric and magnetic fields are going to get switched with some signs, and so it is as far as Lorentz transformation properties are concerned, it has the same Lorentz transformation property, but it behaves slightly differently under discrete under certain discrete operations, like let's say if you reverse the time, okay, if you go from t to minus t, things, if you do things like that, then because of this Levi-Civita tensor, because of this fact, the presence of this thing, this has different transformation properties under discrete transformations, like t going to minus t, compared to what the field strength has. Okay, so that's the point you may want to keep noted. Okay, but let's work out the components. Okay, so there is a very quick way to how to work out the components. Let's say you are interested in the 0, 1 component. Okay, now you are going to say epsilon 0, 1 and this lambda and sigma, this is summed over, and lambda and sigma both should range from 0, 1 to 3. So there are many terms possible, but as you can see, I have written down only 2 terms. Okay, why have I done that? You see, I know that for this epsilon to be non-zero, all the entries must be different and distinct. Okay, otherwise it will be 0. So if they are different and distinct, it will be non-zero, and it will be either plus 1 or minus 1 depending on the arrangement, but it has to be distinct. So if it has to be distinct, then lambda and sigma can only range over either 2 and 3, because the 0 and 1, that has already been occupied. Okay, so if it goes over 2 and 3, let's say in the first term lambda is 2. If lambda is 2, then this is 2. Okay, now sigma can also be 2. But again, then this term would vanish because f is antisymmetric, and therefore, also this is antisymmetric. So, there cannot be any 2, 2. Okay, so they have to be distinct. So the only possibility is either this is 2, lambda is 2 and sigma is 3, or lambda is 3 or sigma is 2. Okay, that's the only 2 possibilities that are there. Okay, and therefore we have 2 terms. And then if we read off the components, F23, in this way. So again, if we know the F mu nu lower, then the F mu nu upper can be found out by multiplying the etas appropriately, and then we see essentially what happens is this sign flips. Okay, it's the F0i that gets a minus sign because there's one spatial index here. Okay, there are the Fij kind of terms, they don't flip because there are 2 spatial indices, so there are 2 signs. Okay, coming from the eta. But so these things remain intact in the upper form when I raise the indices. Then these things remain intact. The F0i indices, these things, they just flip the sign. Okay, so this is the matrix form. If I write down the raised form of F mu nu. Okay, so now you can see that what is the F23 term. So for 2-3, you have to go to the second row and for 2-3, so 2-3, you have to go to the second row, and the 3 is the 4th column here, so that's bx, so that's minus bx here, right, and so on. So you just read off the components from here and fill in these things so that you get the result. Okay. So once you do that, then you can read off these kind of terms. So you do that again and again. So the way I told you, now when you have 0, 2, then these 2 indices can only be 1, 3 or 3, 1. And therefore, these are some combinations of 1, 3 and 3, 1. It always combines to give you one component of the electric or magnetic field. And I have essentially worked it out for you. You can go through the steps and see if you agree. Okay. So if you agree, then these are the various steps. So as we see here, the 0, 1, 0, 2 and the 0, 3 components of F tilde, they are given by the magnetic fields. Whereas now the spatial component, the Ij components, F12, F13 and F23, they are given by the electric fields. Okay, they are given by the electric fields. So a flip happens between the electric and magnetic field as far as F and F tilde is concerned. Okay. So, this is the one in the matrix form. This is the one. This is the F tilde in the matrix form. And okay, just a comment. This, if you are comparing with Jackson, for instance, it differs from that by overall sign because in our conventions we have taken this to be our convention. Epsilon 0, 1, 2, 3 is 1. Okay, you could if you could say that the epsilon 0, 1, 2, 3 is 1. In that case, if you lower it, epsilon 0, 1, 2, 3, that's going to be minus 1, okay, because there are 3 spatial components, okay. So this is the convention of Jackson, okay. My convention is slightly different, and I have, called the 0, 1, 2, 3 as 1, okay. So as far as the tensorical properties are concerned, it doesn't change, it's just a, overall multiplicative factor in overall minus 1, in defining the dual tensor, okay. So, so this is the thing. Very good. So if this is the thing, then these are the components. Sorry, these are the components. And as you can see, the electric fields and the position of the magnetic fields, they are flipped. Okay. In fact, you can exactly write down that the electric fields become minus the magnetic fields, and the magnetic fields become the electric fields. Okay, without a sign. Okay, that's what happens. And again, the factor of C is, you have to adjust accordingly. Okay, because there's a factor of C in the electric field and there's no factor of C in the magnetic field. Okay, so this is what the two things are, and this F tilde, this also has a name. It's called the dual field strength tensor. Okay, so we have now seen that there's a 4-vector potential, there's a 4 current, there's a field strength tensor, which is basically the electric and the magnetic field, and then there is a dual field strength tensor, which is also the electric and the magnetic field with exchanged E's and B's. Okay, very good. So these are the covariant quantities. So now there's one thing that happens immediately. Okay, so there's an identity satisfied by the dual field strength tensor that immediately, as soon as we define this dual field strength tensor, one identity follows. And what is this identity? So it's because lambda sigma, this is antisymmetric, and there's this F lambda sigma, this I can write out in terms of the potential in this way. Therefore, you see that these are different order compared to this. So I can flip it here, I can make this lambda and sigma, and then I'll get a plus sign here. So they will add and they will cancel this factor of half here, and this I can write it in this form. Okay, so this object is exactly equal to this if I write out the field strength in terms of the 4-vector potential. Once I do that, something becomes obvious, that if I take a divergence of this dual field strength tensor, then it vanishes. How does it vanish? Then this del mu, this index must be contracted with this if I'm taking the divergence, and then this mu index is contracted with this mu index here in the epsilon. Now, if I have, I can take, epsilon is just a constant, ones and minus ones and zeros, so I can bring it out, and this del mu will purely act on this quantity. So this will be, there'll be a del mu del lambda a sigma. Okay, but now notice that if you exchange mu and lambda here, then you don't get any sign. But if you exchange mu and lambda here, then you get a sign, and these indices are summed over. So essentially this quantity therefore is minus of itself. Okay, so just if you are not following this, just to make this argument clear, you see what is going on. So I have an object which is epsilon mu nu lambda sigma del mu del lambda a sigma, right? Okay, so now let me write it with a sign. Let me bring the two indices together and write it with a sign. So basically, I can write it as simply, I can pull the sign out, and I can write it as nu epsilon mu lambda sigma del mu del lambda a sigma. This I have done at the cost of a sign. I have pulled the sign outside, and so now if I look at this quantity, and what I do is I exchange mu and lambda. Okay, so I exchange, for the first step is I exchange mu and lambda. If I exchange mu and lambda, then I get a sign. I can write nu lambda mu sigma and the sign comes because of the exchange of mu and lambda, right? And so the sign goes away. Now I can always again interchange here mu and lambda. Here I can interchange mu and lambda, okay, without any sign. Okay, I can just interchange mu and lambda without any sign. So if I do that, then this becomes epsilon nu lambda mu sigma del lambda del mu a sigma. Okay, now you might think that this quantity is different from here. This quantity is different. You might think that this quantity is different from this quantity. But you see, then this is a dummy index. Lambda is a dummy index. I can call the dummy index anything. The mu is also a dummy index. I can call the dummy indices anything. So I can just relabel mu and lambda, okay, and interchange them just by relabeling them. I'm calling lambda mu and mu lambda, you know, I'm just relabeling. Okay, so this is like, then this becomes mu lambda sigma, then this becomes mu del lambda a sigma, and so this is relabeling. Okay, relabel mu and lambda. Okay, so this is there, and now I can again pull the nu inside. That is going to give me a sign. So that is going to give me a epsilon mu nu lambda sigma del mu del lambda a sigma. Okay, so this always happens. If indices are contracted in such a way that there's a antisymmetry in one and there's a symmetry in the other, then that object has to be minus itself. And because this object, as you can see, is minus of itself, and therefore it has to vanish. Okay, so that is the main argument why this object vanishes. Okay, and this object vanishes identically. Sorry, this object vanishes identically, and so as soon as I define my dual field strength tensor, this object vanishes identically. Okay, so this is just the algebra for this. This is just the algebra for this step. Okay, and if it vanishes identically, then we can say that the divergence of this dual field strength tensor is 0, and this is true as an identity. Okay, this is true as an identity. So now let us try to decode what this equation stands for, or what this identity stands for. Okay, we can try to. So there are, as you can see, this mu index is contracted, and this new index basically runs over 0, 1, 2, 3. Sorry, this new index runs over 0, 1, 2, 3. Okay, so these are essentially 4 equations. And what do these 4 equations stand for? Let us try to decode that. Okay, we can try to decode that because, you know, we know what the components of f tilde are. Okay, this I have written here, f tilde lower, f tilde upper. These are the components. Okay, I have carefully kept track of the signs and written them here. Okay, so as you can see, as with f, it is also same with f tilde. So if we bring both the indices up, then only the f0i and the fi0 components, they are affected, as you can see. Okay, their signs change, and this part remains intact because there are 2 spatial indices I and j. Therefore, you get 2 minus signs, which gives you a +1. Okay, so they are not affected, these components. Very good. So now let us look at the time component of this equation. For the time component, you see this mu and nu can run over. For the time component, this mu and nu can run over 0, 1, 2, 3. Sorry, this one can run over 0, 1, 2, 3. And so f0, 0, that's 0 because of the antisymmetry. You know, f0, 0 is 0. And then you're left with del I. This is basically the 3 divergence, fi0. And fi0, as you can see from here, fi0 upper. So these are the components. That is just equal to minus of divergence of b. Okay. So if this is minus of divergence of b, and if this is an identity that this has to be 0, then it would imply that divergence of b must be 0 as an identity as soon as I express the field strength, or the dual field strength in terms of the 4-vector potential. So you see, I want to highlight the fact that this identity was derived because we express the dual field strength in terms of the vector potential. Okay, in terms of the, if I write it out in terms of these components, it is not clear whether the divergence is going to be 0 or not. But as soon as I write it in terms of the vector potentials, it is immediately clear that its divergence should vanish. Okay, so you can now get the hint. This is exactly what happened. There were two Maxwell's equations which immediately became an identities when we express the electric and the magnetic field in terms of potentials. Okay, and this is what is happening. As soon as we write down the field strength in terms of the potential, I can define a dual field strength whose divergence must be conserved. Okay, so one equation for that, the time equation for that, is the divergence of B equal to 0 equation. Okay, that we already seen. So you can guess what is the spatial part of that equation will be. That should come out to be Faraday's law. So you're doing something wrong if it doesn't. So essentially, now I'm looking at the spatial components. Let's look at the first component. So the first component here would be given by, so here the first term will be time derivative of f0i. So f0i, if you go back, f0i, that is given by the magnetic field here. Okay, bx or b1. Okay, the one component. Okay, and then here the spatial divergence will be on f11, f21, and f31. F11 is 0 by antisymmetry because f is an antisymmetric thing. It is 0. And f21 and f31 is basically the z component and the y component of the electric field with the right sign, so that this becomes the curl of the electric field, the x component of the curl of the electric field. So that is given by, so the x component is given by y ex del y del y ez del z ey. That is the x component. So that goes in here. Okay, and therefore the one component is essentially the x component of the curl of E plus del B del T. So similarly, you can check the 2, 3 components also gives us the other, 2, 3 components of this particular vector here. Okay, this particular vector combination. So basically, this is equal to 0 means that the Faraday's law is implied as soon as we write down the field strengths in terms of the potentials. Okay, so this is the same story that happened before. It's just that now it is happening with 4 vector potential and the 4 tensors. So very good. So this is one equation. You see, so this many lines just gets contracted into a simple set of equation like this. Okay, very good. So this is the thing with if you understand the underlying symmetries, then the laws get simpler and simpler. Okay, in some sense. Okay. What about the Maxwell's equation with sources? Okay, so for that, we note the fact that these are the field strength are the electric and magnetic fields, and we would need like some kind of a derivative on them to give us the other two Maxwell's equations. And we have seen that this del mu f tilde mu nu gives us one set of Maxwell's equations. Okay, then there is it is natural to wonder and natural to check what is the divergence of the field strength itself. So the divergence of the dual field strength is 0 by identity, and this gives us a set of four of the 8 components of the Maxwell's equations. So now let us check what about the divergence of f mu nu. Okay, so again you can go through the same algebra once more. The time component. So if you work the time component out, you will see that this becomes the divergence, and f I0 upper, this is exactly equal to the electric field. Note, this is not f tilde anymore, this is the f. Okay, these components are the electric fields. So basically this divergence of the time component of the divergence of the field strength, that is basically precisely the divergence of the electric field. Okay. So very good. So now, right. Now, if you take the spatial components, again looking at the one component, so this gives me a time derivative of the, again, f01. So f01 is basically this one. So this is Ex by C. Okay. And these two vectors, these two components are essentially the z component and the y component, and they fit together to form the curl of B here like this. And here this one becomes the time derivative of the electric field. Okay, so you can check check whether I have read off correctly the components here and I have the right signs that you should check. And also you should verify that the other two components, the 2 and 3 components, they give the right components of these vectors. Okay, so they don't give something else completely. I mean, yeah. So basically, this is what is going on. That now we see that these the divergence of the field strength is giving us the left hand side of the Maxwell's equations, and of course then in addition to this there are sources, and the sources also form a 4 vector, as I said, including the current density and the charge density and the current density together. They form a 4 vector, and this object forms these two components. So this is the time component and this is the spatial component. Okay, missed a vector sign here. Okay, so very good. So now then you can immediately write that this is your Maxwell's equation with the sources. Okay, because this is the left hand side. This is the left hand side. These are the left hand side for the time and the space, and these are the right hand side, the time and space of the Maxwell's equation. Again, this mu naught is there for dimensional reasons, and it gives us the right Maxwell's equation. Okay, so as you can see, there's a factor of 1 over c here, and there's a factor of c here. So this I get, and I get a c square times rho here. So here, right. Yeah. So what I'm saying is, if you match, so this thing, the time component, if we match this equation, then I have a mu naught times c squared, okay, in the time component, and this mu naught times c squared is nothing but 1 over epsilon naught. Okay, so that gives us this particular epsilon naught here. This particular epsilon naught here. Right. Sorry. And sorry, 1 over epsilon naught. Yeah, so this is 1 over epsilon naught, and that essentially is basically this epsilon naught here. Okay, very good. So this is the story then. This is the whole story that you have. So the story in short is that there are 4 currents and the 4 potentials. If you take the 4 potential and write down its curl, you get the field strength, and the 4 it's a 0,24 tensor or a 2,04 tensor, depending on how you write the indices. And once you have the field strength, then you can immediately define the dual field strength with the epsilon tensor. And the dual field strength, the divergence must vanish as an identity. Whereas if you take the divergence of the field strength and set that to equal to the current vector, the 4 current vector, then that is the Maxwell's equation with sources, and the identity that was there, which is this identity where the divergence of the dual field strength vanished. That identity gives the other set of 4 Maxwell's equations. Okay, so that's the story. That's as simple as that. The whole game fits into this kind of a picture. Very good. So again, the conservation of charge equation, that also fits in very well in this game, because if you take this equation, this is the equation of Maxwell's equation with the sources. Now if you take a divergence of this, there was one free index, the new index is free. So if you take a divergence of this, then you see here, again, you have symmetric, because these derivatives can be interchanged without a sign, whereas this is antisymmetric. So this must be equal to 0. So if this is equal to 0, then the 4 divergence of the 4 current density, that has to be equal to 0. Okay, so this statement just follows from the Maxwell's equation with sources. Okay, and if we decode this, then we can clearly see that right. So we can clearly see that this is the time component, and again this factor of c cancels with this factor of c here. This is x naught, so that cancels, and then you get basically the local charge conservation equation. Okay, and this is the statement of the local charge conservation equation. So the local statement of charge conservation essentially becomes a statement of the four divergence free condition of the four current. Okay, and that is why, because this is a conservation law, therefore this current here whose divergence vanishes is sometimes referred to as a conserved current. This is some terminology which is used. It's called a conserved current. Because, so a conserved current, this is just a terminology which by which we mean a conserved current is one whose four divergence is 0. Okay, it's a four current whose four divergence is 0. That's what we mean by a conserved current. And it is called a conserved current because it is related to a conservation statement, a local conservation statement like this. Okay. Okay, so I hope this point is clear. What about gauge transformations? Now next, let us get to gauge transformations. So we know that the gauge transformation for the potential, the components of the four potential, or the vector potential and the scalar potential, that the transformation happens in this way, right? This is the gauge transformation, right? So if this is the gauge transformation, and this is the vector form, and this is the covector form of this object, okay? And so if this is the covector form of this object, then right, then this covector, as we can see, goes over to the phi. The phi changes by minus del chi del t in this way. Okay, and there's a 1 over c in the definition, so it remains. And the a, that goes as plus divergence, plus gradient of chi. And because there's a minus sign here, so this is minus a minus grad chi. Okay. So now, as you can see, you can take this one and this one. These are the time and space components, and you can take them out like a four vector here. And then this one and this one, you can also, this is the time component and the space component of another four vector here. Okay. And as you can identify, this four vector is nothing but the four gradient of the scalar field chi. Okay. So basically, the statement of gauge transformation is essentially shifting the four potential with the four gradient of a scalar field chi. Okay. So this becomes some simple expression like this. Okay, gauge transformations. Okay. So, but again, you have to remember the sign a little bit, because this is the lower one has the minus sign in our conventions. Okay. Very good. So this is gauge transformations. How does the field strength transform under gauge transformations? That's the next question. So the field strength is given in this way, and this is the, so if it transforms, so this arrow means we have performed the transformation. So the four potential has been shifted by the four gradient of some scalar. Okay, in this way. Okay, so this index is basically the same index as the mu. This index is the same index as the a mu, because that's what it has to be. Okay, it shifts by this four gradient. Okay, so once we do that, we see that these two terms here essentially are the same terms, because there's a mu and a del mu. You can always interchange them. So this term and this term is identical, except that there's a difference in sign. This one has a minus sign and this one has a plus sign. So these two things cancel here. Okay, and we are left with the same object as we started off. So basically the field strength is invariant under gauge transformation. As you know that it had to be the case, because the field strength essentially is expressed in terms of the electric and magnetic field, and the under gauge transformation, the electric and magnetic field remains invariant. So this is the equivalent statement in terms of a four tensor. It's the same statement in terms of a four tensor. Okay, so that's what it is. Right. Right. Now, let's see. I mean, because this is the field strength tensor is invariant under a gauge transformation, it immediately means that the dual field strength is also invariant, because under a gauge transformation, this object does not change under a gauge transformation. Okay, this is just a ones and minus ones and zeros. Okay, so that's more or less what it is. Now, let us see what the Lorentz gauge, what does that mean? So we will use this condition in order to write down the retarded potentials, right? We've used this gauge condition in order to write down the retarded potentials. So let us check what this condition means. Okay, so this was the Lorentz gauge condition, if you remember correctly. If you remember, then here there is a c square. One c you can write as phi by c, the scalar potential by c, and the other c you can take and multiply this t here. Okay, so then you see this becomes a derivative with respect to x naught, and this is a scalar potential, and this one is just the divergence of A that remains as del I AI. So this combines in a nice way to write to the form that it is the 4 divergence of the 4 potential. Okay, so the Lorentz condition can be written down covariantly as the 4 divergence of the 4 potential. Okay, notice that this is a perfectly covariant condition. That means if you change frames, the condition remains the same. But you could have also chosen the Coulomb gauge, by which you just set the divergence of A equal to 0. Okay, this is the Coulomb gauge condition, right? Now that Coulomb gauge condition is not invariant. It is not invariant under a gauge transformation. Okay, so if you set Coulomb gauge in one frame of reference and you go to another inertial frame by boosting, then you will see that the Coulomb gauge condition is no longer satisfied in the new frame if you transform your A's, accordingly. Okay, so the Coulomb gauge condition is not respected it's not covariant, so it's not respected if you do a gauge transformation. But the Lorentz gauge condition is respected, or it's covariant, and therefore, if you want to see manifest Lorentz invariance, or if you want to see manifest relativistic covariance, then it is better to choose the Lorentz gauge rather than the Coulomb gauge. Okay, so this is therefore a very, very canonical choice, which makes the symmetries manifest even in the solutions for the potentials. Okay, so that is why Lorentz gauge is chosen, because it is covariant. Okay, so with that, now let me move on to another interesting fact about the field strength and its dual. So you know that you can take vectors and tensors and contract them in some way to make them relativistically invariant. So vectors are covariant objects. If you take them and contract it with some covector, as you know, if you take them and contract it, let's say with some covector, you form a invariant. Okay, so these are invariants. Okay, so similarly, you can take a tensor and contract it with another tensor, it will be invariant. You can contract it with itself also. Okay, by contraction I mean this process of, by contraction I mean that you do this process of taking the indices and summing it via the metric. Okay, so one is a vector index, the other is a covector index, and you set them equal and sum them. Okay, that's what I mean by contraction, and this is the way in which you can get invariants or objects that does not transform under Lorentz transformation. So I hope you understand the difference between covariant object and the invariant object. Okay, an invariant object is something that does not transform at all. A covariant object, like a vector or a tensor, is an object which transforms nicely. It has some particular properties under which it transforms. Okay, it transforms like a vector. Okay, very good. So this is another very important point. Now going on to the next point about going over to the next point. So we want to now, let's say, take the field strength and try to see if we can. So if we contract it with itself like this, then this is obviously going to be an invariant. Okay. So what is this invariant? So if we write the components out, and do this sum, over the indices, then we'll see what it comes out to be. Okay, so you can just read off. See, firstly, there's a factor of 2 because all these individual terms I could have written down in a different way. So this term I could have written down as F10, F10 as well. Okay, I could have done that. So that gives me this factor of 2. Okay, I am not writing that other version. So this gives me the factor of 2. And then if I include this factor of 2 and not write those other version, then I have like 6 terms here. And if you, so all these are like squares, as you can see. And if you read out the coefficient, it comes out to be e square minus b square. Okay, if you keep track of the signs, this is essentially, again, up to factors of c for dimensions, but this essentially comes out to be e square minus b square. Okay, so in natural units, I mean, if you say c equal to 1, then e square minus b square is a Lorentz invariant. Or if you have the c not equal to 1, then e square by c square minus b square, this object is going to be a Lorentz invariant object. Okay, so this is again just some dimension business, but the physics is contained in the fact that e square minus b square is a Lorentz invariant. No matter what, no matter which frame, inertial frame you go to. Of course, if you rotate, they don't change because they are the magnitude of vectors. So rotations will not change them. They are the magnitude of three vectors. So rotations is not going to change them. Neither does Lorentz transformation if it is occurring in this particular combination, that it is e square minus b square. Okay, so that's the first invariant that you could construct out of f mu nu, f mu nu. Okay, if you wrote down f mu nu, f mu nu together. Now what about f tilde? The dual is there, so you can take the dual and then contract with f. You can perform this operation. Okay, so if you perform this operation again, you can write down the dual, the components of it. You can write down the components of the field strength tensor and the dual tensor, and then you can perform the same thing. Again, the factor of 2 is because this term can have 2 forms. This is 1, 0 and f1, 0. That term is also there because mu and nu run over 0, 1, 2, 3, completely. So, that term must be included. So there's a factor of 2 here. And again, there are 6 terms here. But if you keep track of these 6 terms, you will see that they combine into what is E dot B. So it's just twice E dot B. So that's like 4 times E dot B, apart from this factor of 1 over C, which is there because it's there in this electric field. Okay. So this object here, F tilde, contraction between the dual field strength and the field strength, that object is E dot B, and this is a relativistically invariant object. So you see both this one and this one is a relativistically invariant object, and not only it's relativistically invariant because it is expressed in terms of the electric and magnetic field, it is also gauge invariant. Okay, so these quantities are invariant, they don't transform at all under rotation and boosts or under gauge transformations. Okay, I'm bringing that gauge transformation up because you see we could write something like mu, right? And so this is also a invariant under Lorentz transformation. So this is a Lorentz invariant. Okay, this is a Lorentz invariant, but it is not, it's not gauge invariant. And we know that all the physical quantities of interest are essentially gauge invariant as well. Okay, so therefore, since all of physically interesting quantities are gauge invariant, therefore I'm choosing not to look at these kind of relativistic invariants or Lorentz invariants where there's a mu hanging in there. Okay, because if the mu is hanging in there, then there's a very good chance that the object is not gauge invariant, and if it is not gauge invariant, then it is not of physical interest. So therefore, I am not listing such quantities involving mu's. Okay, but of course there can be one term which is f tilde mu nu, f tilde mu nu. Okay, it's the f tilde square or the dual field strength square, and if you express this quantity also in terms of the E and B, you will find that it is again expressed in terms of these two quantities. Okay, It's expressed in terms of E square minus B square and E dot B. So this is not a new quantity or an independent quantity. Okay. So it can be essentially expressed in terms of this one and this one. So therefore, again, I have not worked it out, but you are encouraged to work out the components of the dual square also. Okay. Very good. So I'm leaving that as an exercise. Okay. And here again, I have mentioned I'm not considering quantities like this because they are less interesting because they are not gauge invariant. Okay. Very good. So these are objects that are Lorentz invariant scalars and also gauge invariant. Also gauge invariant. Okay. Now that we have understood the four vector structure of the potential and the electric and magnetic fields, we can use our knowledge about how the covariant objects transform under Lorentz transformations or boost transformations to work out how the potentials and fields transform under boost transformations. Okay, we have discussed in the previous video that if we have a boost transformation like this as we have here, okay, then, sorry, if we have a boost transformation like this as we have here, then the coordinates transform in a particular way. And not only the coordinates transform in a particular way, I mean, if you remember, this coordinates transform in a particular way to keep the interval invariant. And not only the coordinates must transform in this particular way, it also implied that, the way we defined the four vectors and four tensors, the tensors and the vectors must also transform in some specific way. So depending whether its index is upper index or a lower index, depending on that, their transformation properties are fixed. So now if we say that our four potential is a four vector, then we know how its components transform. Okay. Similarly, if we say that the electric and magnetic fields are components of a 0,2 tensor, then we know how they should transform under boosts. Okay. So we are going to use that knowledge about transformation of vectors and tensors under boosts to figure out what is the transformation of the potentials and the fields if we do a Lorentz boost. By a boost I mean that I have an inertial frame S and I have another inertial frame S prime or S bar if you like. Okay, I like the bar better. Okay, I'm putting a bar here. Okay, so you can take the S and the S bar, and the S bar is moving with respect to X with a constant velocity V along the X direction. Okay, it is moving with a constant velocity V along the X direction. Okay. So that is the scenario, and the coordinate transformation under such a scenario is given here. This is the forward transformation and this is the backward transformation. This is the inverse of each other, and they differ just by the sign of the beta. Again, because I'm writing it here for the first time, as you all know, beta is V by C and gamma is basically 1 minus beta squared to the power minus half. Okay, so that's our objects here in this transformation. Okay, right. Okay, so very good. So now let's look at the potential. So the potential in the bar frame or the primed frame, they are related with those in the unprimed frame through this transformation, right? We have seen this. This is how four vectors transform. Okay, and if we therefore work out how this, work out the various components here, then you basically get this, and this is essentially identical to what we have here. Essentially, if you see, okay, so the vectors essentially transform like the coordinates. I mean, you can just do this. I mean, this one transforms like the differential, and this one transforms like the derivative, as you can, as we have discussed in the previous class. And that essentially gives us these transformation properties. Okay, both of them you can use to figure out the transformation properties. It's easier to use this because this is just like the coordinates, and therefore this one is this, this transformation, and from here it is easy to write this down just by taking beta to minus beta. Okay, the inverse, the inverse of these set of transformations. Okay, so this is a boost along the x direction. Okay, that's very important. It is a boost along the x direction. It's important because if it were the boost along y direction, then this A2 would have gotten involved with A0 and A1 would not transform. Okay, so A2 with A0, then A1 would not transform if this was y. Okay, that is very important to realize. Okay, whichever direction it is in, okay, that spatial component gets involved with the time component. Okay, very good. Now here is a example. So the next thing that we will do is to work out how the electric and the magnetic field transform. But before we do that, because we now know how the potentials transform, let us do an example. Okay, so this is absolutely crucial. Okay, in this course, this is one thing that you have to learn, how the potentials and the electric fields transform under a Lorentz group boost. Okay, this is going to be one of the most important takeaways from this course, if you like. Okay, so therefore, I'm doing an immediate example. But please do practice this a lot. Okay, whatever example you can think of, you can just take that and boost it along one direction and try to understand what the electric and magnetic fields are in the boosted frame or what the potentials are. Okay, like I'm doing it for the point charge now, you can take any other solution, any other static solution, and start moving it with constant velocity and examine what the potentials are when it starts moving. Okay, so that I will encourage you to do a lot. In this lecture, I'll just cover one example, which is the boosted point charge, something you have already solved before. Okay, and I'll try to establish a connection with that solution. This will not only tell us how simple it is to perform these kind of transformations, but it will also tell us or teach us. This is an example where we can get to verify our previous formulas that we have derived for the boosted point charge. Okay, whether it is consistent or whether we derived it correctly or not, so that we can verify. Okay, that is what we are going to do now. Very good. So now, if you take this case, so let's say that the charge is at rest in the S prime or in the S bar frame. Okay, then in that frame, the potential, the scalar potential is basically q by 4 pi epsilon naught 1 over r. Okay, this is the potential there. And please note that here these are the bar coordinates. So this is x bar, y bar, z bar. Okay, and the vector potential is 0, identically. Okay, so now if we know how the potentials transform, then the new potential in the new scalar potential in the unprimed coordinate or in the S frame. So in the S frame, the charge is moving with constant velocity v along the x direction, right? So therefore, the potential, the scalar potential is given by gamma times the potential in the unprimed frame. Okay, sorry, in the primed frame. Gamma times the potential in the primed frame. This is the potential in the unprimed frame. Okay, so now, so this is very clear. This is gamma times the potential here. This is immediately obvious. And I can just take the previous formula here and just plug it in here, okay, to get the answer. Okay, I can plug it in here to get the answer. Okay, but there's a very important problem or a very important point that in the unprimed frame, in the S frame, this is x, y, z, and t. These are the coordinates. But in the primed frame, x bar, y bar, z bar, and t bar, these are the coordinates. Okay, so we have to make sure that we not only implement this transformation between potentials, but we also implement a coordinate transformation so as to express this entirely in terms of x, y, z, and t instead of the bar coordinates. Okay, I hope this point is very important. I hope this is clear. Okay, what is going on? Similarly, we can see that A1 has this form, that this is the transformation. This transformation has been picked up from the transformation of the potential that we just derived. Okay, this is the form of the AX or the X component of the potential. And as you can see, because this is 0, this is also given by gamma times beta times phi bar, where phi bar is the scalar potential in the primed frame or in the S bar frame. Okay. So now, if I take this and write it again, this is the point. Here, x, y, z, and t. How did I miss t here? I don't know. So okay, is x, y, z, and t. This is the coordinate in the S frame, and that it's not only we have to make a transformation of the components because these are vectors. We also have to make a transformation of the coordinates of which these are functions of. Okay, these things are functions of the coordinates, and the coordinates also have to be transformed. So there are two things that we have to do if we want to find the potentials in the S frame. Okay, and of course Ay and Az is 0 because both Ay and Az in the unprimed in the primed frame they are 0. So in the unprimed frame they are also 0 because they are just identical to the primed. These components are unaffected when we do a boost along the x direction. Okay, so that is something which is 0. Okay, very good. So now if we now analyze this, so the scalar potential, let's see. So it's q times gamma by 4 pi epsilon, and these are the bars. So if these are the bars, we know what the coordinate transformation is. The y and the z does not transform because the boost is only along the x direction. And the x components here, that gets mixed with time in this way. Okay. And then this thing is just ct, where that t is basically this time here, right? Right. So we can just express it in that way. Okay, this is the x square, and this is the y square and the z square. Okay, and it's only, this factor of gamma is here. This gamma comes from the coordinate transformation, and transformation of the coordinates, that's what this gamma comes from. And this gamma comes from the fact that there's a change, the potential is related to the other potential by a factor of gamma. Okay, that comes from the way in which vectors, the 4 vector potential transforms. Okay, so this gamma source is the transformation of the 4 vector potential, because this is the time component of a 4 vector potential, and this gammas and this particular change comes because there's a we have also have to change coordinates. Okay, not only the vectors themselves. Okay, the coordinates needs to be changed as well. Okay, so basically you can take this factor of gamma outside because there's a factor of half here. The power of half here. Therefore, this gamma will cancel, and we are left with this y square plus z square divided by gamma square here. This is the result for the potential in the frame where the charge is moving with a constant velocity along the x direction. Okay, that's just 2 steps to figure out what it is. Okay, you remember we had taken so much pain in while doing the moving charge analysis. It was way more complicated. Okay, but this is much more easier to do it this way. Okay, so this is, if you like, what we are doing is a solution generating technique. Because we know how things transform under boosts, we can use a solution which is static and then boost it to get a new solution. Okay, and since it's just transforming, we don't need to solve the equations once more to get a new solution in the boosted frame. So we know solutions where things are static as well as when things are moving with constant velocity without solving any equations. If we know the static solution, we know the solution where things are moving with constant velocity just by a coordinate transformation and a vector, the vector transformations, etc. How it happens in Lorentz transformations. Just by implementing that, we'll be able to figure it out. Okay, I hope this point is clear. Very good. So now, whatever the AX component, it's also the same, just that this factor is different now. There's a gamma beta by C. So gamma beta by C, this beta I am writing V by C, and this epsilon naught C square, that gives me a factor of mu naught in the numerator. Okay, and here the velocity remains as the velocity here, and the denominator, the same thing happens with the denominator as it happened with the scalar potential here. Okay, the same thing. Okay, again the factor of gamma cancels. This factor of gamma cancels because I'm pulling it out. Okay, and this y square plus z square gets divided by gamma. Okay, that's the solution. And Ay and Az is equal to 0. So that is your potential, or your Lenard-Wickard potential for the moving, that is your Lenard-Wickard potential for the moving charge, or it's the potential for a charge moving with constant velocity. Okay, it's not moving with arbitrary velocity, but it is moving with constant velocity, and this should be your Lenard-Wickard potential. So let's now go back to your Lenard-Wickard potential answer and try to match whether you have the right answers, or whether you had the right answers when you derive the Lenard-Wickard potentials. Okay, that has to be matched, and because we have to match that, therefore we see let's do that exercise. Okay, that requires a little bit of complicated algebra, but we have to do that exercise. So let's take this. This was the, if you go back to the previous lecture on Lenard-Wickard potential for a moving charge, you will find that this is the answer. Okay, this was the Lenard-Wickard potentials. Now this V out here could have been anything. It could have been a function of time, but in our case, the V is actually a constant velocity. Okay, just to remind you, this kappa factor was this factor. And clearly, this kappa factor is greater than 0 because this is r hat, this is a unit vector, and the components of v must be less than c. So this is 1 minus some quantity which is less than 1, so this has to be greater than 0. And not only this, the magnitude of r, because it's the magnitude of a vector, that also has to be greater than 0. Okay, so so basically, we want to emphasize the fact that this denominator out here must be greater than 0. Please keep it in mind. This will be helpful. Okay. So this r, kappa times r, this thing must be greater than 0. And apart from this, we have to use the retarded condition. So just to remind you what the retarded condition was, it said that you have to. So these are, if you like, these are functions. Let me. This is important. So I will write it out once for you again. So if you like, these are functions of x, y, z, and t, and this is a vector x, y, z, and t. But these objects here inside, they are not functions of the same t here. They are functions of t tilde. And what is t tilde? You have to solve this equation for t tilde in terms of t and then plug it back into this expression for t tilde. Okay, so these are functions of t tilde, so you have to evaluate it for t tilde and then you have to solve here this one and plug it back in here. Okay, so just to remind you, what was r? The r vector was this vector r. This is, this r hat was essentially, the r vector was essentially x I hat y, y j hat plus z k hat. Okay, this is the same x, y, and z which is there in this formula here. It's the same x, y, and z. Okay, and then this w was the trajectory of the particle. So the w is vt times x because it's moving along the x direction. This is the x hat is the direction. Okay, if you like, you can make it I hat just to avoid a complication here. Okay, make it I hat. Okay, so velocity is along the I direction and it is constant. Okay, independent of time. And the position vector, therefore, this one, the x coordinate, its x coordinate increases with time proportional to v. So it's vt. So the charge is moving along the x direction with constant velocity. Okay, that this one is his trajectory. Okay, so this is w of t. Okay, and so r is defined as r minus w. That vector is the r vector, and the mod of that vector is this thing. So if you write down its the r appropriately, then it's x minus vt plus y square plus z square. But this one is t, but as a function of t tilde, it's t tilde. Okay, that is something which you must note, that it is a function of t tilde. Okay, so very good. Now we are interested in finding k times r retarded, which is the denominator here. In both the expressions, there's a denominator, which is k times r retarded. Okay, so we have to write these objects out and then you solve the retarded condition and plug it back in here. Okay, this is the retarded condition which you need to solve and plug it back in there. Okay, so this is our expression for kr retarded. Okay, which has to be greater than 0. And this is the retarded condition which we need to solve for and plug it back in here. Okay, here we know the players because we know what is r, everything. We know what is v, we know what is w, so we know what is r. And so we know everything here as a function of time, t tilde. But our objective is to now solve this equation and plug it back into here. We also know this object because we know what this r is, right? We know this object as a function of this thing. Okay. So therefore we know everything and we just need to do the algebra. Okay, so first note that the retarded condition here, r t tilde, can be written in terms of Ct minus T tilde. Of course, this is the retarded condition, so we can solve for it. So if we solve for it, then this Kr retarded, this R here, okay, this R I have multiplied in the K. I hope you realize that point. So I can take this K and multiply it with R here, then this becomes R, and then this hat goes away and this becomes a vector. Okay, that's exactly what I have done, okay, in writing this. So now this R, the magnitude of the R vector, that can be written in terms of Ct tilde times T minus T tilde. So that I have substituted here. And this one, I know V is along the X component. So this is the Rx component of the R vector. So the X component is nothing but X minus V T tilde. Okay, this is what I'm going to take and substitute in here. Okay, so let's do that. So that's what I have done. Okay, that's what I have done. And V by C, again, I have denoted by beta. Okay, and then I have just rearranged, taken the T tilde together. Okay, these two terms I have bunched together as T tilde. So there's a factor multiplying 1 minus beta square, which I have written as C by gamma square. Okay, gamma is again 1 over root over 1 minus beta square. So so that I have used here. And here again, Ct minus Bx, this is another term that remains. Okay. Now we really have to solve for this T tilde. Okay, we have to solve this equation for T tilde. Okay, so this is slightly algebraically intensive, but you can do it. Okay, you can do it. Just remember these notations, and so we are writing out the R completely in terms of x, y, z, and T tilde completely, and then square both sides here. You take this and square both sides. After you have squared both sides, then you get this thing here, and this is just a minus b whole square, that thing written out. Now after this expression, you again do this whole squaring. You get 3 terms here, and this whole square gives you these 3 terms here. Okay, now you combine them as a quadratic equation of T tilde. So this is a T tilde square b T tilde plus c equal to 0. So this is a quadratic equation, and this I have again algebraically simplified it. By dividing with this a, I could divide it throughout. Again, note that this factor is basically a 1 minus beta square is this factor is nothing but c square by gamma square. So you can multiply by gamma square by c square throughout, which I have done. As you can see, gamma square by c here, because there's one factor of c here, and there's a did I miss a gamma square by c square? I think I did. Right. So I have missed a gamma square by c square here. Okay. And then here this is minus b plus minus b square minus 4, a is 1, and here I have the gamma square by c square. Okay, perfect. So here it's correct. Okay. So here once I have this, then this is the solution of T tilde. I will take this T tilde and plug it back in that original expression. But as you can see, because I have solved a quadratic equation, I have 2 solutions. And this sign, essentially, I should keep the sign for which this T tilde is the retarded time. Okay, compared to T, it happens earlier. Okay, it's the retarded time. So that we have to, that is the physical thing that goes in determining the sign. But we are going to, we can do another simple thing, instead of figuring out which is greater or less, we can do something simpler, which is eventually we want this k of r to be a positive quantity. So we'll retain the sign, for which this k of r, this object is a positive quantity. Okay. So I have kept both the signs, and this is my T tilde. So if you remember, this k of r was 2 terms. One term was this, and the other term was c by gamma squared times T tilde. So this T tilde, I have solved this quadratic equation and substituted it here, and there are all these terms. But notice that this first term in the quadratic solution to the quadratic equation, this cancels with the term that was there initially. Okay, so there is a nice cancellation happening, and then this object is just this quantity multiplied by c by gamma square to the power half. This is k, this is kr, and because I want this quantity to be positive, therefore I drop the minus sign here. I have kept only the plus sign. Actually, I have kept the plus sign here, drop the sorry, I have kept the minus sign here and dropped the plus sign because there's a minus sign outside, so the minus would make it minus plus. And so I've kept the plus sign here so that this object has to be positive. Okay, that's what I have done. Very good. So now this is the expression. Okay, this is the expression to the power half. So it's resembling close to the denominator we had when we did the transformation. Okay, it's very much similar now because if we you see this here there's this r square. If you remember, while writing it out, we had this x square plus y square, right? So this combination, this is what we had called r square, and that remains there in the solutions. Okay, that remains there in the solutions everywhere. Okay, so now here we have these terms, and there's r square. So essentially, I have pulled out a factor of gamma to the power 4 by c square, cancelling this, and then here this c square goes out, and there's a 1 over gamma square remaining, because here there's gamma to the 4, but here there's gamma square. And then now this gamma square, 1 over gamma square, I've replaced by 1 minus beta square. And once I have done that, then I have written all the terms out. Okay. And not only I have written all the terms out, this r square also I'm writing out as x square plus y square plus z square. Okay. Even I even did that, and then club the x squares together. So you see there's a x square here, there's a x square coming from this r, and if I club them together, then I get beta square plus 1 minus beta square. These two cancel, and that gives me a coefficient of x square, which is just x square. Okay. And then the y square plus z square, that remains into this term. So this is the term. And then there are other terms, which is this term and this term. These two I have written here. Okay, these are the two terms. Okay. Now, if you notice that there's a x squared plus v squared t squared from here, v squared t squared. Okay. And so, this v squared t squared is this one here. Beta square is v by c. So this is v squared t squared. And then there's a minus 2 vtx. So this combination is nothing but x minus vt, the whole thing squared. Okay. So this denominator now, therefore, has exactly the same form as we had in the denominator in the case of when we did the transformations. Okay. So therefore, I can write phi is this object retarded. Once we solve the retarded condition, this is exactly the same denominator as we had. And for the a, of course, this v of t has to be evaluated, but this is super simple because v doesn't depend on time. So this is just the x vector. It's v is along the x direction. So it's v times I. It's the same denominator here. So no more work to do. It's the same denominator, and the mu naught here is naturally there in the original solution. So the mu naught remains. So this is identical to the thing that we get from Lorentz transformation. You see, algebraically also Lorentz transformation was so simple to do, and here we have to do a lot of solve quadratic equations, etc., and then derive this result. But eventually it matches. Eventually it has to match if you have done it correctly. Okay. So I hope this was somewhat illuminating exercise. This also demonstrated how you could deal with this retarded condition. Okay, it is a slightly complicated scenario. We didn't do a lot of problems with implementing this retarded condition, but this is a demonstration where I have implemented the retarded condition for the moving point charge. Very good. Now let us consider the boost transformation for the electric and magnetic fields. Okay, that is also easy to do. Right, that is also easy to do because we know how a 2, 0 tensor or a 0, 2 tensor transforms. So this is exactly the transformation properties, if you remember. So these are the factors that you get from how the infinitesimals transform. Okay, and that way you can just figure out what are these factors. And now it's just a job of writing out things completely. Okay, so there is a sum over alpha and beta, and so given mu and nu, this index gets fixed, and there's a sum over alpha and beta that you need to do, and you have to crunch out the algebra. So I've done that for you here. So you see, let's say I want the f10 in the transformed coordinates, in the barred coordinate. If I want f10, okay, then how does this go? Then I use x bar 1 and x bar naught, and then alpha and beta has to be summed over. But now you can play a trick. It's a very interesting trick. You see, you notice in this transformation for boost along the x direction, the only things x1 depends on, x1 bar depends on, is x and x naught. So alpha can only take 1 and 0 value. So I start with the 0 value. Okay, then this is a 0, this, if this is a 0, this has to be a 0. But if this is a 0, beta can never be 0. Okay, beta can be 1, 2 or 3. But again, you see, here, because there's a naught here, okay, x naught, that only depends on x and x naught. Okay, x naught bar, that depends on x and x naught. Okay, so this beta index can either be a 0 or a 1. Okay, but it cannot be 0, because if it was 0, then f00 is 0. So it can be 1. So as soon as you say this is 0, okay, this is fixed to be 1. You can also say that this is 1, because there's a non-trivial dependence on x as well for x bar. When this is 1, this 1 is fixed to be 0. So this is everything that you have in this sum. Otherwise, you would have a lot of terms. You're summing over alpha and beta, but this is all you can have. Okay, if you just follow this logic, then this is all you have in this sum, because of the simple reason that you're boosting along the x direction. And if you're boosting along the x direction, then then these are the x naught bar and the x bar. They can only depend on x naught and x. Okay, they cannot depend on y and z, because they are just equal to each other. You can just exploit this fact to write it out in this way. Okay, and then if you just now read off these coefficients from here, then you can read it off, and you will see that this one just becomes gamma. The gamma square you can pull out, then it becomes gamma square times 1 minus beta square. That's just 1. So f10 and f10 bar and f10, they are identical, which means that the ex bar is equal to ex. So the component of the electric field along the direction which you are boosting does not get transformed. Okay, it remains the same. Okay, so the electric field remains the same along the direction which you are boosting, but the other components gets affected, as we will see. So if this is 2, 0, then this is 2, 0. Again, if this is 2, then this alpha has to be 2, otherwise it's 0, because this 2 is y basically. Okay, this y bar is only a function of y. Okay, and that is equal to 1. So this is the only thing that can be non-zero. So this alpha gets fixed to be 2, and this is 0. So this beta index can be either 0 or 1. So it is either 0 or 1 here. Okay, that's how you write it out. Now you can read out these terms from this expression here. Okay, you can read out these terms, and once you read them off and you know what these field strength components are in terms of the electric and magnetic field, once you do that, then you get an expression which says that the y component of the electric field in the bar frame, or the S bar frame, or the prime frame, that is related to EY component in the unprimed frame and the BZ, the Z component of the magnetic field in the unprimed frame. Okay, this just comes out of these transformations. Okay, again, this is something, completely, I'm showing this completely algebraically. You can make some physical arguments, but this algebra is what gives us this transformation, right? So this algebra is you feel like the most fundamental thing, that is, this is the way things transform. Okay, and that is what we should use to figure out what these electric and magnetic fields are. Okay, how they transform. Okay, of course you can say that in a particular situation you can probably solve both sides, that when it is moving or it is not moving, and then you can say that in that particular case this is equal to same. But if you do this algebraically like this here, then it has to be true for all the cases, not just some one particular case. In all the cases when things move, for all solutions, the electric and magnetic field must be related in this way. The y component of the electric field must be related in this way with the y component of the electric field in the unboosted case and the magnetic field. Okay. So these frame transformations, if you like, are the most general transformations that should always happen irrespective of solutions. For all solutions, this should be valid. Okay, so similarly, if 30 is the EZ component, again, you use the fact that alpha in this expression, alpha can be non-zero. I mean, only alpha equal to 3 can this be non-zero. Okay, and if alpha equal to 3, this is non-zero, then this is x naught. So this beta can be 0 or 1. So it is either 0 or 1. There are two terms. Again, simplifying this, you get the Z component in the S bar frame is EZ component, and there's a plus. Compared to here, there's a plus V times By. Okay, and you see, if this is the y component, this is the z component of B, and if this is the z component, then this is the y component of B. Okay, with a plus sign. Okay, so it's kind of I mean, it's so simple that you can remember also. At the end of the day, it's so simple that you can probably remember. Similarly, if you do for the Bz, so you consider F12 bar here, then you have this expression here, 1, 2. Now this is even more simple. You see, there's a 2 and this is beta. Okay, so you see, this beta can at most be 2, so it's 2 in both the cases. Otherwise, it's 0. And this, because this is 1, x bar again, this x bar 1, that is a function of x and x naught. So either it can be 0 or 1. So now, this is all there is, 2 terms. And you just read off these coefficients from in here, and you get this expression. Okay, and again you put in F02 or F01, the corresponding expressions that we have in that matrix there. Okay, that we can put in, and then we see that Bz transforms in this way. Okay, so again Bz goes as Bz, and there's a Ey which again comes in here. Okay, algebraically it just comes in here. Okay, so basically the electric and magnetic fields are getting mixed. That's an interesting thing that's happening. So in a particular frame, as we'll see the point charge again, but if you like, that there can be a situation where there's just electric field, right? Okay, let's say that you have a charge configuration which just has a static charge configuration which gives you an electric field. But if you start moving it now, then there's a magnetic field. If you move it with constant velocity, then there will be a new magnetic field to to that solution. Okay, because the electric field and the magnetic field are getting mixed up, and that essentially is predicted by these transformation equations of Lorentz transformation. Okay, I mean intuitively this is also clear, because if there's a charge and it starts moving, then now there's a current, and that current is going to produce a magnetic field. That's how it happens. Okay, if you are trying to actually solve the scenario. Okay, but here you are not solving any equations. You're just doing transformations. That's all. That's all. Okay, that's a way. If you like, that's a way to get new solutions. If you like. Okay, so very good. And this is what you get for the Bz component. And right. Okay, so we are left with 2 more. So I think By, this is F13, that one. Again, doing the same, playing the same game. Because this is 3, this beta can only be 3, and this is 1, so this can be 0 and 1, and writing it out, you get, this transformation equations. Okay, for By. Again, By is given by By in the unprimed frame, By bar is given by By in the unprimed frame, and Ez comes in here. And also you see, just like the electric field, the magnetic field, that mixing happens with a different sign here, and for Z, there's Y component of the electric field, and Y component of the magnetic field, there's a Z component of the electric field. Okay, so and finally, if you do 2 and 3, so this 2, there's 3, and this alpha has to be 2 or 3. Otherwise there's alpha and beta. Alpha has to be 2 and beta has to be 3. Otherwise this is not. This is going to be 0. So basically this follows from the transformation. So this F2 3, and therefore this Bx is equal to Bx. So both the x component of the electric field and the x component of the magnetic field, these two things, remain invariant. Whereas the y and z components, they get mixed up with each other in this way that we have written here. Okay, that's the summary of everything. Okay, so this is the bar in terms of the unbar, and you can ask what is the electromagnetic field in the S frame or the unprimed frame, how it is related to the primed frame. This you have to invert these relations, okay? And if you invert these relations, there's a simple way to do it. You just write, beta 2 minus beta or V2 minus V, and that's what you just get from this relationship. Okay, if you like, these are the full set of relations. The sign change happens, and these are the full set of relations which gives you the transformation between the electric and the magnetic field. Okay, so yeah, so this is what can be simply derived by doing just 2 lines of algebra, knowing how the field strength tensor, how tensors transform under Lorentz transformation. Just by knowing that, you can just derive how the electric field and the magnetic field transform into each other. Okay, I must pause here for a moment and tell you that, again, I have said this before, but if you go and look up Einstein's original special relativity paper, then he actually understood this fact. You remember, we had this discussion about a magnet. If we have a magnet and a loop of wire, and if we bring the magnet towards the loop of wire, then there is a change in magnetic field which gives rise to an electric field, and that results in an EMF in the wire. Okay, and on the other hand, if we bring the wire towards the magnet with a constant velocity, so the magnet has non-uniform magnetic field, let's say, then the flux inside the area enclosed by the wire, that changes, and the magnetic field then exerts a force on the current carrying conductors, and then even then there is an EMF which is set up. Okay, that EMF is entirely due to magnetic field, whereas the other previous case there was an electric field which was responsible for setting up the EMF, right? So there are these two completely different effects that happens there. Okay, but the EMF produces a current which is identical in both the cases. No matter whether you go and sit on top of the magnet or you go and sit on top of the wire, it's the same physical effect. Okay, so no matter which, so I'm assuming they're moving with constant velocity. So in that case, it doesn't matter in which frame you are in, whether you are in the frame of the magnet where it's stationary, the magnet is stationary, and the wire is coming towards you. In that case, when the wire is coming towards you, the magnetic field is not changing with respect to time because you're sitting on the frame of the magnet, and then essentially it's the magnetic force that gives rise to the EMF. On the other case, where you go and sit on top of the wire, the magnet is coming towards you. That's a change of magnetic time. That's a change of magnetic fields that's giving rise to an electric field, and that is what is giving rise to the same EMF. And essentially, at the back of the thing, if you try to do that more carefully, and this thing, these are the set of transformations that leads. In one frame, the electric field in the other frame, can become a combination of electric and magnetic fields. Okay. So just like, for the point charge, let's say the point charge was stationary, or static, then it was only the potential, the scalar potential that was non-zero. But as it started moving, we saw that the scalar potential, there was a vector potential as well. And that vector potential can give rise to a magnetic field. Or in other words, the moving charge can give rise to a current, which can produce a magnetic field as well. Okay. So I hope that this idea is very clear to you. And the fact that electric field and magnetic field can interchange was lying there in front of your eyes, always. Okay, the fact that they should be able to interchange between themselves. And Einstein took this case, very seriously, and he tried to come up or think about what are the transformations that can actually make this happen. Okay, and then thinking about it logically, he essentially came up with this special theory of relativity. Okay. And the way I'm presenting it, I'm not presenting it as Einstein had done it, but this is I'm kind of combining with our modern understanding, and the way I'm presenting it, like you start with the postulate and then you like move forward, and this is a consequence of the Lorentz transformation. This transformation between electric and magnetic field is a consequence of the fact that electric and magnetic field combines into a covariant tensor, and that tensor transforms in a covariant way under Lorentz transformation. This is a consequence of that fact. Okay. So I hope you appreciate what is going on. Okay, now going back to the boosted point charge, we have done the potential. Now let's look at the fields. Okay, we can look at the fields now. So if we look at the fields, then we know that this is the electric field of a point charge. Okay, and the magnetic field is 0, of course. So I can write out the components of the electric field, Ex, Ey, Ez. Again, in the S prime frame, the charge is stationary at the origin, let's say, and it's moving. So from the point of view of the S frame, there's a charge which is moving along the x direction at a constant velocity v. Okay, that is the scenario. It's the same scenario that we considered before, just a while before. Okay, again, there is this Ex, Ey, Ez. This is given by this r hat. So r hat I have multiplied by r on both numerator and denominator. So I have a 3/2 here, and this is the r vector, which I have written in a column in the writing out the components in this way. Okay, so now let us look at the Ex component in the frame where the charge is moving. This is the S frame. Okay, that is given by the Ex component because it's the same thing. So then this is going to be exactly like this, but as we know that x bar is given by gamma times x minus vt. This is the, we also have to transform the coordinates now, like we did for, you remember in the case of potentials, it's not only the change of the vector components, it's also the functional dependence on the coordinates that needs to be changed. So if we change the functional dependence on the coordinates, the x bar is given by this, and then there's this term, and we can take the gamma outside common. This gamma, which also now comes from the transformation, cancels with the gamma in the denominator, one gamma in the denominator, but this is 3 by 2 here. So there is gamma cube in the denominator. So this gamma square, this gamma cancels and makes it gamma square in the denominator. Okay, and then this expression, if you remember, was just kappa times r retarded. Okay, this expression was just that. Okay, but now this is kappa times r retarded cube. This cube is very important. Okay, it's now cubed because this is 3 by 2. Okay, for the kappa times r, this was just 3. Okay, so I'm just trying to draw an analogy with what we saw just a while ago. I hope you remember. Okay, so now the EY component, if we look at the transformations again, the EY component is going to be given by the EY component, but with a factor of gamma. And this magnetic field, because it is 0 in a static frame, so these terms are 0. We can forget about them. Okay. So the EY and the EZ component of the electric field is given by the EY and the EZ component of the electric field in the static frame, in the frame where the charge is at rest, multiplied by a gamma. That's it. Okay, it's just a gamma factor multiplication. Okay, so this gamma factor multiplication is there, and so for our case, we not only have to multiply by gamma, we also have to do a coordinate change. Okay, so if you do the coordinate change, y bar now doesn't change; it becomes y, but then there's this x bar here, and this gamma now comes from this transformation here, okay, between the components of the electric field. Even now, then you have the identical denominator, which is basically gamma squared times kappa times r, this thing cube, okay, retarded, okay, if you remember. Okay, so this is the denominator here, okay, and this is the z component, also the same story, there's not much difference between the y and the z component, okay, it's identical. So there's the same denominator here for the z component as well. In the numerator, there's a z and there's a y. That's the only difference. Okay. So very good. And for the magnetic field, the x component of the magnetic field is identical. So its magnetic field is 0 in the frame where the charge is at rest. So this is just 0. But the y component of the magnetic field has contributions from the electric field from the static case, right? So this is the case. This is the frame where the charge is moving. So in the frame where the charge is moving, the magnetic field is non-zero, as I was trying to tell you a while ago. And so there, this is given, this is because of the fact that in the static case, the EZ component is non-zero. Okay, this term is 0, but the EZ is non-zero. So I write it out. Then there's this factor initially. The minus sign is there, okay, because of this minus sign here. And then there's this factor of gamma again. If I do the coordinate transformation, I can just pull out the gamma again and write it in this way. Okay, this one of the gammas cancel here because this is gamma to the 3, that cancels with one numerator. And this beta here, which is a new ingredient here, so this beta remains as V, and this epsilon naught times C squared, that becomes a mu naught in the numerator. Okay, that's all the algebra is. So similarly for Bz, okay, there's a very identical exercise for Bz. This is not there because in the static frame there's no magnetic field, but there's an electric field, and this contributes here in this way, but there's just no sign now, and this is y, okay, instead of a sign, and instead of the sign and y, this thing was z here, okay, and there was a sign, additional sign. Exactly, we have the identical algebra. The denominator is again, this is the most noteworthy thing, the denominator is gamma squared. If we remember the previous calculation, kappa r retarded, this thing cube, okay, this is the form of the denominator. Okay, very good. Let's just remember that and let's proceed. So I've written the summary of these. These are the electric and magnetic fields of the moving charge with a constant velocity. Okay, these are the expressions. Okay, written all the components. I've written out all the components. You can ask whether I can write it covariantly or not. So that I have already written previously while writing down the Lenard-Weikart potentials and fields. So now the point is that that form, that covariantly vector form, whether that reduces to these expressions, that is something you can cross-check. Like we cross-checked for the potential, you can cross-check it for the fields as well. So for the fields, I'm writing down only the terms in the expression for the fields of the moving point charge, the terms which are proportional to velocity. Okay, because acceleration is 0 because the charge is moving with constant velocity. So I have set all the acceleration terms to be 0 and I've retained the velocity fields. So the velocity fields for the electric field is this, and the magnetic field is this. Okay, and so as you can see, the denominator already works out. Okay, so here I have just multiplied by a factor of r in the numerator and denominator, so this became r vector here, and this became, you know, v times r here. So the denominator becomes kappa r cube times gamma square retarded. This is identical to our denominator that we got. And here also, if I multiply by r in the numerator and denominator, this becomes a r vector. This formula is something that I have just picked up from what we discussed previously for the moving point charge. Okay, so you can consult that. I've set acceleration to 0 in that formula and picked it up. I've set acceleration to 0 because here we are considering a charge moving at a constant velocity. Okay, so that's what I have done. I have picked this up, and then there's a multiplication with r in the numerator and denominator, so that the denominator becomes kappa times r whole cubed, you know, with the retarded condition. You know, that again, it's the same set of things, same set of algebra. And if we do that, we can directly use this fact that this retarded thing is this. Then the denominator, you know, exactly matches our expected denominator. And in the numerator for the electric field, I have this expression here. Okay, so I have this expression. This is the r vector, this is the v vector, okay, times r. Again, r, I can use the retarded condition itself. You remember the retarded condition? The retarded condition was r t tilde, you know, t tilde plus r t tilde by c equals to t. Okay, this was the retarded condition, and that I can use back in here for r here. And once I do that, this r vector is simply so this is the nature, right? So you see, I've written down all the components. So v vector is non-zero only along the x direction. So this is the x. So this vector I have written like x, y, and z components. So the y and z components simply are the r vector y and z. You know, these are the simple things that just goes in here. This is ry component and rz component. The x component, this is the x component here. Okay, this is the x component here, but it has, you know, I have used the transformation, so it's x minus v t tilde. Okay, this is a function of t tilde. But then there's a v times r, and this r is essentially c times, you know, this difference. So the c cancels the denominator, and it's v times this. And then you see the t tilde just cancels out. So if the t tilde cancelled out, the numerator is independent of t tilde. So you don't have to use the retarded condition there, and it is just this thing. So the electric field, the numerator is this vector. So this is the x vector, y vector, z vector, and x component, y component, and z component. And then the denominator is this. This is identical to what we just got by doing a frame transformation. Okay, this is identical to that. Okay, so similarly, for the numerator for the magnetic field, this is v cross r. Okay, this is v cross r vector, and v is only non-zero for the x component. It is 0 for the y and z components. Now, if you just take the cross product, you can do it in any way. If you are expert with epsilon ijk's, you can do it that way, or you can do it this brutal way. Okay, which is writing it out, and this brute force way. So if you write it out, then you see that there's a there's a j component and a k component. The x component is not there. Okay, because x component, you know, this is all 0. Okay, and that's why bx is 0. So the x component is 0. And the y and the z component, you know, essentially differ. You know, this one has a sign, this one doesn't. So if you remember our previous result, this is exactly the form of the b vector that we have. The denominator again is precisely kappa square, gamma square times kappa times r whole cube, which is to be obtained after putting in the retarded condition. Okay, so this we did before for the potential, and you know, we just picked it up from there, and this algebra is identical to that. Okay. So I hope that the fact this matches is very satisfying. I think we've got all our signs, etc. right. So so we are in business, and so we can take these formulas for the transformation of the electric and magnetic field, and we can try to generate newer solutions. Okay. So you know, this is very important. You know, this thing is very important. This is one of the main takeaways of this course. Okay. I cannot emphasize how important it is. This idea is one of the main important takeaway that you are learning from this course. Okay, very good. So you know, I'll give you some assignment problems, but you know, try to practice as much as you can, or you know, think about it as much as you can, So that, maybe this is something completely new to a lot of you. So you should try to think about it. All right, so that was the electric field and magnetic field story. The potential also, we've seen how it transforms. So one thing we have completely left out in our discussion is what happens to the Lorentz force. So what happens to the Lorentz force? Okay, so can we write it covariantly? Because that was another thing that we, we started off just assuming it without justifying it at all. We just started off assuming it, and that is one of the fundamental equations, if you remember. So we have to understand how this Lorentz force takes the form. So basically, the Lorentz force takes the form in this way, that it is given, this 4 vector. So if you take the field strength and take this new index and contract it with the current here, this is what gives you the Lorentz force. So if you write this component out, you will see that this is given essentially, this should come out to be proportional to rho times the E vector. So this, the time component of this, the space component, should come out to be the space component, that should come out to be, so space component is mu equal to I, 1, 2, 3, okay. So mu equal to I, that's the space component. So that should come out to be proportional to up to factors rho times E plus B times, J cross the current cross B, okay. Please check this if this is true. I'm going to do the same thing, assuming the current for the point charge. So this is the force density. Now if we write down the force for the point charge, then essentially this J I should replace with Q times the 4 velocity for the point charge. Okay, so this is the current density, and therefore this is force density. Now this is the force because Q times U mu is the 4 current, if you like. Okay, so I have, in this way, I have that, therefore you don't see the delta function. I'm just integrating over the delta function over the location of the charge and writing the current out. Okay, so so now this U is this 4 vector that we have described in the previous video. It's the 4 vector. It's a velocity 4 vector for the point charge. Okay, so it's the velocity 4 vector for the point charge. And if you remember, U takes this form if you write it out. Then U takes this form. Please see the previous lecture where we have derived this. Okay. So now F mu nu, again, to remind you, it has this form with the electric and the magnetic fields. So let's write the components out. Now we are experts in doing that. Okay, the space component, if we take the space component 1 here, okay, then basically what do we have? So when this is 1, this nu can be either 0, 1, 2, or 3. When it is 1, then it's a 0 because F is antisymmetric, so that's 0. So there are 3 terms here which are non-zero. They're all non-zero. And you see, one of these terms gives me the x component of the electric field, whereas these 2 terms kind of come together to give you the V cross B term. Okay. So if you evaluate this, you get, E vector x component, V cross B x component times Q, which is the usual. Okay. But here you have this additional gamma factor. Okay. This covariant expression has this additional gamma factor, okay, which you never had in the Lorentz force formula. Okay, this just comes because you're trying to write this covariantly, and therefore in the covariant expression there is this additional gamma factor because the velocity has this gamma factor in it built in. Okay, the covariant velocity. Okay, remember, this is very important. The V does not have good transformation properties. It transforms in a very, very weird way, but gamma times V transforms properly. So if you're looking at covariance, you better multiply with this gamma. You should not forget it. Okay. But then what? Were we doing some non-relativistic stuff at the, so far? What were we doing? Why didn't we keep this gamma? Why doesn't, that appear? Okay. So to answer that question, we have to look at the Newton's laws. Okay. So if you see our free particle discussion of our free particle in the previous lecture, then you will see that the Newton's law for the free particle was mass times 4 acceleration, that is equal to 0. Okay, so in the presence of this force, 4 force if you like, okay, then this mass times 4 acceleration must be equal to the 4 force that we have written here, right? That should be the modified Newton's law if you like. Now in the modified Newton's law, this acceleration, 4 acceleration is given by du d tau, okay, and here you have this expression, F, this 4 force is q times F contracted with the 4 velocity here, okay. So now just if we write the space components of it, so set mu equal to I, okay, 1, 2, 3, then you see this object essentially becomes gamma times v inside here, okay, these components are gamma times v, but this tau also gives rise to a factor of gamma here outside, okay, and here you have this factor of gamma coming from this covariant expression for the force, okay, we just derived it a while ago, okay. So these two factors cancel out, and then you see ddt of this object is equal to this. So there's this only one modification inside, which is this gamma factor inside, okay. If I write it out, then you see there's a modification of this gamma inside, and the rest of the thing, this is just the usual expression for the Lorentz force. So we have been right throughout, given the fact that this gamma cancels with the gamma on the left hand side, if you want to write both right and left side covariantly. So remember, without the gamma, the components of the force, that has very bad transformation properties. But with the gamma, this transforms covariantly in a nice way, okay. So does this one, without the gamma, this is time and not proper time. So it's not invariant, okay, this time is not invariant, okay. So this transforms weirdly. But then with the gamma, this is proper time and that is invariant, okay. So that is the interesting part. If we remove the gammas, then it looks closer to the equation that we are usually familiar solving. But without the gammas, there is no covariance as such. I mean, there is a covariance. I mean, if you just multiply with the gammas, it becomes covariant. Okay, but the covariance is destroyed from the individual sides. It's no longer vectors we are talking about. It's weird quantity, or components of vectors we are talking about. It's weird quantities. Okay, this point is somewhat important. So I hope you appreciate it. Okay, but the bottom line remains that Newton's law is modified because of this factor gamma inside. And if you can identify this object gamma mv, this was nothing but the momentum for a relativistic particle. Okay. In the non-relativistic case, this gamma is close to 1, and then we have the usual equation to solve for, Newton's law, where a charged particle is experiencing a force in terms of electric and magnetic fields. Okay. So the bottom line is we have identified the Lorentz force, and we have identified the Lorentz force. This is the force density, and this is the Lorentz force for a point particle. Okay, that is what we have identified the the covariant nature of the Lorentz force. Okay, so one thing I didn't tell you purposely, and I will not tell you, I would really like you to think about it, and it is this fact that if we write this equation, okay, then there's a we've talked about the space component. So this is a vector equation. There are 3 equations, 1, 2, 3. Okay, corresponding to the 3 components of the space vectors. But this is a 4 equation. So this is a 4 vector equation. So there are 4 components. There's a time component particularly when these two are 0. Okay, I want you to work out what that component is, and I want you to understand what that component is. Okay, so I've given you a hint here, which may be interesting. I don't know if you would like it, but you see, we have seen that if we take m times u mu, this object, then this m times u mu, the spatial part of it, that is gamma times m times v. Okay, that is basically the momentum of a relativistic particle. Okay, but the time component of it is gamma times m times c, which you can write as gamma times mc square by c, which is basically energy by c for the relativistic particle, free particle. Okay, so this I want to give as a hint. This doesn't answer this question. What happens to the time component of this equation? But this is somewhat a hint that if you take the 4 vector, for the 4 vector, the momentum and the energy together combine to give you a 4 vector. Just like we have seen here, the charge density and the current together gives you a 4 vector. the scalar potential and the vector potential together gives you a 4 vector. Similarly, energy and momentum, they transform into each other, and they transform into each other as a 4 vector. Okay, that is something which we can just take away from the formulas of the point charge. Okay, sorry, not of the point charge, of the free particle. Okay, if you just analyze this thing for the free particle, then this is one thing that we can take away, how energy and momentum transforms. They transform together as a 4 vector. Okay, so with that hint, I want you to figure out what is the zero component of this equation and what is its physical significance. Because that is something new. You have never, our Newton's law were just 3 equations for a particle, right? So now we have a time component as well. So what is that saying? Okay, what is that time component saying? So that I want you to figure out yourself. Okay. Okay. So now there are 2 very important applications. I'm going to give this to you in your assignments, but I wanted to say a few words. That's why I've written it up here also. So you see, let's say now you have a charged particle moving with a, some constant initial velocity v naught. Okay, in some xy plane. Just let's say you have just the xy plane. It is moving with some constant velocity v. This is some v naught. Okay. Okay. Now let's say you apply an electric field along the x direction. Okay. And you want to know what the trajectory of this particle is. This particle is a charged particle. Because this particle is a charged particle, then this becomes a problem of solving a particle with constant acceleration, because you would say that the particle is moving with constant acceleration, and so because there is a force on it, constant force, so it moves with a constant acceleration, and therefore in this region you can expect that the particle moves with a constant acceleration, so its trajectory is going to be like a parabola. Okay, that is you might expect. That is what you will get if you solve your original Newton's law. Okay, that parabola expectation and the fact that moves with a constant acceleration, etc. That is just a fact which follows from Newton's law, a non-relativistic Newton's laws. But now you have a relativistic version of the Newton's law, which is this one. Okay, I want you to use the relativistic equations. These equations. Okay, I want you to use these equations to resolve this problem of the trajectory of a charged particle in a uniform electric field. And you will find that the trajectory is very interesting. It's very different from a parabola. Okay, in general. Okay, it's like x goes as cos times lambda times y. This a and lambda you can determine in terms of the velocity, the electric field, etc. I want you to determine. Okay, so you have to basically solve the modified equations or the modified Newton's laws to find this solution. Okay, and or this trajectory. And if you take this, set your initial conditions appropriately so that there are no x naught, etc. here. X naught, there can be y minus y naught. That is you can set the initial conditions appropriately that it is not there, and then this is the equation. And only you will see that if this contains the v, the relativistic velocity. Okay, if you do a non-relativistic expansion of this, you will get back the parabola because this cos is going to give you a y square. Okay, that is the idea. Okay, then you get back the parabola only in a non-relativistic limit. Of course, if it is a non-relativistic case, then this gamma here is just 1, and in that case, you just have the usual Newton's law. Okay, you will have a parabola. Okay, but otherwise, it's this cos. Okay, that I want you to solve for. So this is the motion of a point particle in a constant electric field, which you have to solve the modified Newton's equation for this. I'm giving you this as a problem. It will be in your assignment set. Okay. So similarly, you can solve the problem for a constant magnetic field as well. Okay, and if this is also I want you to solve it. Okay. So I will provide you with the solutions, but give it a go initially. Okay, if you take these solutions and if you if you try to find the trajectory in a constant magnetic field, then you get basically again the equation of a helix. This is the equation of a helix. So if a particle is moving with a constant initial velocity in a region where there is a constant magnetic field along the z direction, then you basically perform some helical motion in the z direction. Okay, so that just comes out of solving even the relativistic equations that I want you to demonstrate. Okay, and determine all these constants. This lambda naught and w. Determine in terms of the initial velocity and the magnetic. The value of the magnetic field b. So please determine that. And so these are the two problems which I really want you to solve once you have understood how the relativistic Lorentz, relativistic correction to the Lorentz force equation of the Newton's law. Once you understood that, these are the two things which you should be able to do. Okay, so here I'll stop for this video. In the next video, I will basically discuss how this structure, this covariant structure, emerges from a Lagrangian, okay, or a minimization of an action, okay, or extremization of an action, okay. So how a variation principle can lead to these covariant equations, that is going to be the topic of our next video. But for this video, let me stop here. Thanks a lot for your attention.